So hello, everybody. My name is John Lakos. I work at Bloomberg. I've been there for 24 years, so quite some time. And what I hope to talk to you today about is what Bloomberg and hopefully other people are doing to help make C++ safe. So we'll get started. Uh, this is another slide. This is a lot of slides, a lot of layers of slides here. So you probably read the abstract to figure out to come here. So I'm not going to read the abstract, but there is one difference. So I put it in green. It's not just C++26. This is a roadmap for how we're going to get to make C++ ultimately safe. And by safe, I mean two things. I mean safe to use, and I also mean safe from other successor languages. So that's the goal. So we'll get started. What's the problem? Well, C++ has come under a lot of criticism lately. I'm sure you understand. Rust is a successor language. There are others. And people are very interested in using languages that give you compile time safety. That's not a surprise. On the other hand, there are companies that have been using C++ for, like Bloomberg, uh, since the turn of the century, if not a little bit before, and some even longer than that. So you know, it's a problem. Anyway, there are a lot of different agencies, government agencies, uh, people in the White House have been talking about it in previous administrations. So, it's a problem. And major companies are backing away from C++. In particular, Google is leaving C++, openly moving to Rust, and has other things like Carbon. Microsoft is no longer uniformly supporting WG21, and that's unfortunate. This is internal disagreements as to what the most effective thing to do is. However, of course, Microsoft uses C++ extensively, so they would certainly be interested in improving C++. And Adobe is quietly moving new development over to Rust. In fact, I understand that by the end of the decade, 90% of new development is going to be in Rust as of now. So what's our top level strategy? Reinvigorate C++. And I think if you saw Herb's talk, there's a lot of work to try to do that. And I think it's very exciting, but we still have the problem of other languages purporting to be safer than C++. So the way we're going to do that is by making C++ safe, healthy, and efficient. C++ always has to be efficient because of the interest in Rust. Some of the interest in moving C++ forward has left and gone to other languages. And so that's part of that healthy part. But what we're going to talk about mostly today is what is the problem with safety and categorize that. So the three primary areas of focus: safety, what does that mean? Correctness and security. And health, well, we're talking about the ecosystem, generally the compilers, but also the other supporting tools. And then efficiency. And there are two parts to that. There's the machine efficiency, but there's also the human efficiency. And I think what you saw with what Herb was talking about, there's a lot of, with reflection, there's a lot of opportunity for human efficiency with that. So making C++ safer. Correct. The essential behavior is as intended. By the way, essential behavior is a term of art. It means what is it that when you call a function, what do you expect to happen? There are other things that happen that might be behaviors that are not expected, but the essential behavior has to be what you expected it to be. So we need support for detecting and preventing defects. We also need to make it secure. So this is an example of where we want to, as Herb discussed, not have something inadvertently exposed that would otherwise be usable by someone who's trying to attack our system. So in any event, we want to make it secure by default. In general, we want to make it safe by default. So, healthier, compilers, libraries, supporting tools, the ecosystem. Again, standard library implementations, sanitizers and such. And testing frameworks. So these are all parts of what makes C++ usable. It's not just that the compiler is cool, but we need to have the whole ecosystem working together. And then making C++ more efficient. Well, it's already very efficient. We want to make sure that nothing gets between C++ and the hardware. So programs and supporting tools run quickly. So that's just in the process of doing your job. You want things to work quickly, executables, compilers, linkers, and so on. We also want the human being to run quickly. We want them to be efficient. And I think artificial intelligence is going to make a very large difference in how fast we're able to write and verify code. But this is not about AI, so I will skip that. What we aim to achieve is making C++ easier to use safely and correctly by default. And that means for people who don't know exactly how to use the tool as experts, we don't want them to be caught out by having something bad happen. So closing the gap with other safe languages is part of making it better for people who already have C++, not to have to go to another place and work with other languages, Rust and so on and whatever. We want them to stay here with us in C++ and continue to do their job and be effective. And improving the typical user experience, of course, setting an example for other organizations. So, other organizations. I really would love it if other people besides Bloomberg would want to partner with us to try to help make C++ safer, healthier, and more efficient. And that means actually getting together and funding the work that needs to be done with compilers, because compilers don't write themselves, and larger organizations have been reducing their efforts. So anybody who has any interest in working with us, I'd be very interested to have you guys do so. All right. This is a medium to long-term achievement effort, and we really want to try to get this to work as best we can in the long term. We're making good progress now, but we can do better. So I wanted to go over what it looks like for people to start with an idea and then take it all the way through to using it in production. So Timur is going to give a talk. He's giving the keynote tomorrow. I took this from his previous talk at ACCU, and I'm going to go through it just very quickly. We started out with a long time ago with the first proposal, and it didn't last very long. And then a little bit later, we had another proposal, and this was by me, and this was macro-based. And so it had a short life, but it didn't quite make it. And then finally, it went away, and we started the new one. And it went down in flames, actually, in plenary. We started the new one, which made it all the way to C++20. And then there was a whole discussion about, well, did we get it right? Is it okay? Is it not okay? Whatever. And then, well, we started the SG21. And SG21 is the contracts study group. And we spent 6 years. And just very recently, it was voted into the standard. That was in February. And right now, we're about here. And now I'm going to talk about what Bloomberg's done alongside of what's been visible outside. So in 2003, the BD team developed a macro-based contracts approach. And then it went into production in 2004. And then in about 2009, I took what we had and I productized it so that it was something that people could use in general. Not that it wasn't very good before, but just to make it with all the usage examples and so on. And then 2012, we open sourced it. So this particular approach has been around for, you know, what do I want to say, 13 years. It's been around for forever, but it's been available for like 13 years for people to use. Then in 2015, we noticed something problematic, which is that we couldn't use contracts in a uniform way, contract checks. So we decided to create something, and in fact, this was the review version of it. So instead of enforcing contracts, we instead review them so that they are no longer uh, the same level of enforcement. Sorry about this. I have a I have a little bit of jet lag. I apologize. Many papers were written, and then we did much work on the reflector. And then in 2022, Bloomberg sponsored many features in Clang. And I'm just going to say this. I'm sorry. The important part is we are now sponsoring this, and so this is actually a very big deal. So the way it works in production, we start with creative thinking, and then something happens and it doesn't work. And so we start another thing and we make it to the C++ standard, and then it works for a little while, and then we start prototyping it. And then stuff happens, and you'll see that we get feedback from our prototyping, and then that comes down, and we have compiler prototypes, and it comes to the C++ 26 standard, and then from then on, everything's working. Okay, so then it gets to the point where you actually have compiler implementations, and then we get into production use. And as you can see, there's a big timeline, and it takes time to get from each point, from one to the other, and then eventually, after 10 years, we've gone from an initial idea to actual production. And then we get more feedback, and so on, and eventually things go on. Now, that's the way we're doing it now. Canonically, we'd like to do better. So we'd like to be able to just come along and start something, and then get compiler prototypes, and then over time, get feedback, and then eventually we get to the standard, and that's good. And then shortly thereafter, we get to annual compiler versions, and then proceed forward. And then get to production, and here we are. Now, this is better, clearly, because we don't have so much time between when we start out with the idea and when we get to production. In any event, this is now 2 years, then 1 year, then 1 year, and now we've done it in 4 years. So this is the way the process normally proceeds. Ideally, what we'd like to do is we'd like to be able to go from an idea. As soon as we get it into the language, we'd like to be able to do production use. And then after a little bit of time, when we get the compiler version approved, we're ready to go. So this would be ideal. Okay, so what does it mean to be safe? So safety means different things to different people. So secure is one kind of safety. Does it admit security vulnerabilities? Well-defined, does it admit undefined behavior? Correct behavior, does it do what we intended it to do? Surprisingly, correctness isn't typically considered part of safety. So, and it should be. What is memory safety? So it's a language is memory safe if it does not permit access to unallocated or uninitialized memory. Have people heard the term memory safety? Yeah. Okay. So garbage collected languages, Java, Python, JavaScript, Go, those are all garbage collected languages. Functional languages, C#, Scala, OCaml, Haskell, and PHP. Languages that enforce the law of exclusivity, okay, LOE. And these are Rust via borrow checking and Swift via reference counting. So, but anyway, a language doesn't, just because we have memory safety doesn't mean that we have addressed all undefined behavior. For example, in this case, we could imagine that we have an int that takes uh, two, excuse me, uh, sorry about this. In this case, we have an example of something that's undefined behavior, and we're not able to, uh, oh my goodness, I'm sorry. Read this slide for a second. Signed integer overflow is UB, but it's not a violation of memory safety. Where are we trying to achieve? We're trying to achieve security and correctness. And these are two different aspects of the same basic idea. And that is, without changing any source code, if we simply recompile and relink our code using ISO compliant compilers, we can be sure that our core language UB will ever be executed. So what is correctness? What we're trying to achieve. That is, those who choose to check the contracts of their own user-defined functions have the tools to do so. Tools that address C++. These are tools that there is no one tool to achieve all of the C++ UB. Runtime contract checking, erroneous behavior, symbolic contract assertions, profiles, and compile time exclusivity. Runtime enforced exclusivity. So what is runtime contract checking? Safe contracts. What is a contract? Plain language contract, it's a natural language description of the agreement between clients and libraries. Contract assertions. A C++ code contract that identifies something that must be true in a correct program. C++ contracts, most valuable features, preconditions and postconditions directly on declarations. Standard way to, I apologize. I'm having a little bit of an issue because of jet lag, and it's affecting me. This is not my best presentation. I apologize. So 4 standard semantics for contract violations: ignore, enforce, observe, quick enforce. A 5th semantic is anticipate, which is assume. Simple use case. So for example, suppose we have a precondition and a postcondition. So this, we might be able to do better here with the precondition, with the postcondition. So for example, we have a much longer postcondition. In square root, what we're trying to do is observe that the result is within some tolerance. And so postconditions are very hard to write because it's very possible to get them wrong. And if you don't test them, your postcondition might actually be incorrect, and that can lead to problems. So parameters used in a postcondition, well, what does that mean? That means that we need to make the parameter const so we don't change it. That's a limitation that we came up with in the standard, and we need to do that. It means that implementations must not modify their parameters. Now, if we have a square root function and we want to implement it even more carefully, so we can do that, here are our pre and post conditions. Here we have a double output, and here we have the beginning of the implementation. The square root is being used for the output, and we have a contract assert, and now we're going to implement it with this very complicated expression. And the complicated expression is to determine whether the square root that we chose, the standard square root, is as close as possible to the function to the exact value that we're expecting. So if you want to look at this example, it's in Godbolt. Anyway, okay. So the most important usage for contracts is the operator bracket. And so we're going to do that here. And here you can see that if we did that, we would catch about 65% of the problems. We sometimes call contract assertions ghost code. Why would we do that? Why would we call a contract assertion ghost code? Does anybody have an idea? Right. It doesn't get executed at runtime. Um, unless we want it to. In other words, it doesn't have to be. So the point is, contract assertions may or may not get executed. And so, in any event, uh, we call it ghost code because it's not really there. Teaching safe contract assertion predicates. Contract assertion predicates should have no side effects. So what does that mean? Yes. Right. Okay, so contract assertion should have no side effects. That's the basic idea. You want to teach people the basic rule is contract assertion should have no side effects, but the advanced rule is it must have no destructive side effects. And a destructive side effect is a more advanced idea, but contract should be very easy to teach. So if we just tell people no side effects, we have no problem. Destructive side effects have altered the essential behavior of the program. So coming in C++29, the ability to require a contract assertion always to be enforced, to make a contract assertion as expensive, audit, capture input values and use them in preconditions. Employee requires clauses of contract assertions to be easy to use with templates. And here's an example of a contract assertion that's always enforced. Here's one that could be more expensive. Here's an example of a capture. This requires clause on contract assertions to be easy to use with templates. And coming in C++29, assertions is the core language. Assertions in the core language, which is implicit preconditions. Herb talked about this. C++ style array bounds checks. For example, here, this would be a problem. Signed integer overflow checks. We have examples of being an int max and going one too far. A null pointer check. And here's an example. Okay, so core language assertions could come much sooner than C++29 because we don't have to change the standard. So the C++ standard does need to change because implicit assertions replace UB. So then we have erroneous behavior. Now, erroneous behavior and contract assertions are actually cover the same and different things, as we'll see. So what is erroneous behavior? Herb talked about it in the original talk. The point of erroneous behavior is to give to make undefined behavior that has a reasonable but not necessarily correct value correct. So defining unbehavior to guard against security vulnerabilities when contract violations are not enforced. So defining unbehavior, EB is nonetheless guarded by the precondition. So importantly, incorrect use remains observably incorrect. Uninitialized reads. So we saw the example with Herb with uninitialized reads. No more supposedly reading private data, which means that we don't leak those secrets. And here's an example. And so this is subtle because we have an error, and this may or may not be depending on whether G reads the behavior. So here's a Venn diagram. So runtime contracts and erroneous behavior. We have the uninitialized reads in one category, we have the array bounds in the other, and then we have the signed integer overflow in the middle. And so we have unreachable pointer errors as being another kind of error. We have unallocated memory access. We have data races, I'm sorry, and we have erroneous errors due to raw pointer arithmetic. So these are things that are not covered by these particular approaches. So here's another example, symbolic contract assertions. And so core language example, we have, for example, we have this. Now, if you look, we have a symbolic pre that says is reachable. What does is reachable mean? It means that you have two you have a pointer from the beginning and the end of a range, and they're not connected to the same contiguous data. So that's what we have here. And if you look at this symbolic declaration only contract predicate, and you see that this is connected to the begin and the end, um, and local static analysis is able to identify that this is a problem. This is possible only because we put the precondition in that says that this must be true. Otherwise, there would be no way to check this. So then this is a perspective standard container example where you have something very similar and we put the precondition in. And as you can see, uh, it's connected to the first and last. And again, the error can be caught by a simple compile time check. Then we have a harder example where we have array.begin and array and now what we're going to do is we're going to see that right here in a second, there's a problem. And this problem is that we can't really look at compile time to know whether this thing is going to be a problem or not, which means we have to do more work. So it's hard to catch at compile time this kind of problem, but that's okay because we have other ways to deal with things. The next level is profiles. So disallowing C-style casts. So profiles basically are about stopping a type from stopping us from using constructs that are not ideal. They can cause problems. So profiles is a subset of the language, it creates a subset of the language. And here we have this and it's unsigned type safe. So profiles are orthogonal to contracts in the sense that they do not, they are different. And as we'll see with Timur's talk, there's going to be a structure in which these all come together. Timur's talk is tomorrow midday. But the part of the profiles that is a subset of the language, that's what's orthogonal to contracts. So exclusivity enforced at compile time. This is what Sean Baxter is trying to do. And the law of exclusivity, if a storage reference expression evaluates to a storage reference that is implemented by a variable, then the formal access duration of the access may not overlap the formal access duration of any other access to the same variable unless the access are reads. So this is the law of exclusivity. And basically what it does is it helps us make sure that we don't have lifetime issues and that we don't have data races, which is a great thing. So this is an example here where we've got a vector and we want to make sure that we don't have a bug. And so this is ill-formed because if we do a pushback, we're going to have violations. And so even if we reserve a whole bunch of memory, it's not going to matter because that's not a compile time thing. It's still not going to be allowed in a compile time enforced environment. Notice that this is STD2, by the way. That's Sean Baxter's alternative approach. So we would have to rewrite everything. So exclusivity is enforced at runtime. We're going to call that ghost data. So now what is ghost data? And this is something that's really big for C++ and something that we're working on. Additional information made available to multiple contract assertions at various granularities, e.g. all assertions within a particular function invocation that could not otherwise be represented in the abstract machine. Okay, so the idea here is that we're going to retain information just like we do that the functions might not exist. Why do we call this, by the way, ghost data? Before I go on, why would we call it ghost data? So it's the same reason. It might or might not be there. So in a situation where you have um, uh, uh, a program that's trying to catch all the bugs, you would have the ghost data enabled. And then that would help us to prevent any kind of undefined behavior. However, once the program's been debugged, you want to make sure that the program runs quickly. You can remove the ghost data, you can remove the functions, and then the program runs quickly. So this is an important part of what we're trying to do. So exclusivity during iteration, what does that look like? So it's the same example as what we had with Sean Baxter's example. So the ghost data attracts the iterator validity. And now what happens is when you add this function here, there's a runtime check. It remains because we don't know if the pushback happens. We might need to, it might invalidate the thing. And it's only if we invalidate the thing in practice that we get the warning. So the big point of the difference between runtime exclusivity and compile time exclusivity is that in compile time exclusivity, you're limited to what kind of algorithms you can write. And in runtime exclusivity, the only problem happens when you actually have the defect. So this is the important part. This is why we have this very exciting thing called Ghost Data, which we are working on. So notice this is STD, not STD2. So that's the important part. So how does this work? The cool thing is that it's inherently not compile time checkable. And if we do this, this guards against the UB. This makes it impossible for the UB to occur. So we see the interaction between contracts and ghost data. So now cannot be invalidated. So what are the important special properties of ghost data? Assertions can express any requirement whose validation could alter program behavior. Many assertions will require core language interfaces to update it. Ghost data has no runtime overhead when contract assertion checks are disabled. So local analysis can prove that the assertions will not be violated. So this is really cool. Current safety project priorities. Let me just say that again. Current safety project priorities. Thank you. Okay. Safe contracts, EB memory safety, vector array bounds. What does this mean? About 65% of the problems will be solved just with that. And then contract violations, 20%, erroneous behavior, 10%, and the rest are these things. Lifetime issues, 2%, data races, 2%, and other problems, 1%. So we look at integration of our various techniques. Here we again have the uninitialized memory reads, the array bound reads, and the signed integer overflow. Okay, and then we have symbolic contract checking over here, and we have some profiles with bad reinterpret cast, and then we have unallocated memory access, and then we have data races, and all of this stuff can be done here with compile time exclusivity. But then we have these other things that can't be, and here we have runtime exclusivity, which covers everything. So the current project, runtime exclusivity in Ghost Data, is something that we're really trying to make happen. Oh. Other project priorities. So making things healthy. So GCC, Clang, et cetera, trying to make that work. New hardware platforms, new operating systems, the current standard, bug fixes, missing features. These are all things that Bloomberg is trying to help with making better, and we are funding this. And again, we're looking for help with other people, other companies who are interested in preserving the longevity of C++. We want to do experimental language features, adding new features such as erroneous behavior, ensuring timely availability once standardized. Then there's something else. There's efficient allocators. So C++ memory allocators are something that keep us from, or that help us to keep other languages, lower level languages, from getting between us and the hardware. And it was invented at 1998 at Bear Stearns, brought to Bloomberg in 2002 by me. I invented it, I brought it. Scoped allocators were working in C++11, but they were compile time parameters in 2017, now we have the polymorphic allocator, PMR, polymorphic memory resource. So that's working much better. Forthcoming, there's going to be a book on allocators, which is written by myself and Josh Byrne, and more standard libraries support variant and optional, and language-based allocators, rule of zero for allocator-aware types. This is something that we're working on, and the first step is going to be to create something called side channels. This is, again, something that's coming later in the year, hopefully, and something that people at Bloomberg are working on. Oh, so you heard about trivial relocation, and it's a little bit redundant with Herb's talk, I apologize. But it was a secret, so how did I know? So it's basically the same idea, new creating new objects by moving them rather than by relocating them rather than moving them, which means you're going to end the lifetime of the other object. Generalized user-defined reallocation is challenging, but we're working on it. In any event, relocation is a step towards being able to do the kinds of efficient things where we actually get the safety that we want. As an example, well, it allows us not to worry about certain kinds of problems where we have self-referencing types. Here's an example. This is this particular keyword suggests that it's something that we could certainly do if we wanted to. And this is what it would look like. And the important thing here is no destructors or move constructors are called, only mem-move. So that's cool. Relocation improves lifetime control, it increases safety. We have never null pointer types, which is null pointer types are the kinds of things that you can have problems with when you fail to initialize a null pointer. But if the pointer is never null, then this is a good thing. So it can be initialized from the beginning to the end. No possible use after reallocate. It's like move, but better. Layers on top of move semantics. Okay. Compile time reflection. Vast new possibilities for building libraries. This is good. Serialization, hashing, mix-ins. Okay, moving forward. Current project priorities. So this is what we're doing at Bloomberg. We have contracts, and the acronym I'm using, SHE, reminds me that it's safety, health, and efficiency. And so underneath you see we have correctness and safety, E for ecosystem, and M for machine and human. And these little symbols here say the black one means we've really covered it. The yellow one means we kind of touched on it. The white ones mean we might have done something, but we don't really care. Erroneous behavior. So we're working on that. We covered security with that, but we touched on contracts. Memory safety. And so we're definitely, as we look at memory safety, we are covering both correctness and security. Bug fixes and maintenance. Well, bug fixes definitely help a little bit with security, but it's really about the ecosystem. Then C++26 conformance. There's a lot of work to do. I mean, I heard painted a fairly rosy picture of how we're really catching up and implementing a lot of things, but there is a lot of work to do to catch up on compilers and features. And we're doing our best to do that, but we need help. Allocators are mostly under the machine efficiency, but also the human efficiency, especially when we get them into the language. And then we have relocation, which is human efficiency and also a little bit of correctness because there's less to do. And then reflection, and of course that's human efficiency big time. And these are things that we're all working. So summary and conclusion. Basically, we need C++. C++ needs us, and we hear you. Somebody should do something, and we are. The North Star, make C++ such that we can and want to use it 25 years from now. So our top level strategy, maximize the SHE in C++. And again, that's safety, health, and efficiency. Making C++ safer, contracts erroneous behavior and memory safety, making C++ healthier with bug fixes and C++26 conformance, and making C++ more efficient, allocators, machine, trivial relocation, and reflection, human. And again, C++ safety, health, and efficiency roadmap. Here's some of the things that we're doing. And I'll just let you read because there's no point in saying it. And then for completeness, I thought I'd talk about some of the things that we're going to try to do beyond this. So I left a lot of time for questions and answers, especially since I'm really not feeling at all well, and I'm doing the best I can with what I've got. I don't know what I've got, but I've got something. But in any event, just read through these things so that you get an idea of what we're trying to do. The important message here is that there's a lot of stuff that needs to be done for C++. And what I tried to do is give you an idea of what the various aspects are of C++ safety, as in undefined behavior that we're trying to correct, and also the various tools we have for correcting it. And I think the slides much speak for themselves, but I could have done a lot better job at trying to explain them if I weren't so under the weather. Importantly, the best way to predict the future is to create it. And that's what we're trying to do. So we really need help in trying to create this stuff. Want you to join us. And my name is Jay Lakos, John Lakos at Bloomberg.net. And again, I apologize for my not feeling well. This is the first time that that's happened. That's been so bad. Thank you for coming. And there's bonus stuff afterwards, but I want to take some questions because I think I can probably answer them better than I did on the slides if you have any questions. I can go back to slides if you want.
Thanks for the talk. On uninitialized reads, what determines if whether it traps or it reads garbage?
I'm sorry, say again. I didn't understand.
Yeah, for uninitialized reads, you said it will trap or read garbage instead of like sensitive data. So is it a compiler flag that determines which behavior happens?
Okay, I think I understand what you're saying. Let me try to answer your question. So when you have an uninitialized variable, automatic variable on the stack, and you read it today, you read garbage. It's undefined behavior. The compiler can do whatever it wants. And as Herb showed, sometimes it will read garbage. The garbage might be some secret that you read before. It's always undefined behavior. What's happened now is we've made it erroneous behavior, and so that won't happen. What we want to have happen with erroneous behavior is that it's defined to be something. Well, we don't want you to know what that something is. We'd like it to be like it returns an integer, some integer, not garbage, but it returns some integer. And it doesn't have to be the same integer. But what it can't do is be undefined behavior and allow, what am I trying to say? To allow time travel or something like that. Does that make sense?
Yeah, I thought it would also trap, terminate the program, but maybe I misunderstood with erroneous behavior activated. Is there no termination behavior?
I'm really trying to understand what this.
Okay.
No, I just don't understand. I'm sorry.
I must have misunderstood.
Maybe if you could catch me out. Yes. Do you understand? Please.
So I just kept on doing and then you're asking for erroneous behavior traps.
Yeah, I thought like
It does not. Okay, now erroneous behavior simply describes what's going on. That what if you try and read some data from what's been written to, that is defined as erroneous behavior. The compiler might issue a diagnostic. It's not obliged to. There might be all sorts of clues, but it won't stop your code.
okay. Different question.
Sure.
Boost code. When now I implement an operator's bracket, for example,
Yes.
I would have some code inside that checks if I'm outside of bounds. And for example, explicitly terminate my program rather than handing out some garbage reference to whatever. Because I feel in some instances it's safer to terminate the program in such a case. Now, when I migrate to C++26, I could add a contract with a precondition, but I cannot rely that it's there. Is that correct?
Yes. So this is the important thing. The thing about contracts is, and this is the part that I would love to impart. You have a plain language contract. It has preconditions and postconditions, whether it says so or not. You have an understanding of what your function does. Then, when people call it, they have to abide by that. If they don't, the program is broken. What contract checks do is they allow us to detect early on that the contract check is broken. That the contract that the caller has called something that isn't allowed. That's the idea. Does that make sense?
Yeah, but that means to be really safe, I would keep my manual check inside the function and terminate the program.
Okay.
And the precondition, so I now have a duplicate check.
Okay. So now this is the interesting part of contracts. If you want to write code that always checks, you don't need contracts. However, the problem with C++ and not the problem, but the advantage of C++ is that it's extremely fast. So we have the duality of programs that need to be fast and correct. So how do we do that? So the way we do that is we have contract checks that enable you to check that your program is working. Now, initially, you saw what Herb said. He said that we put the stuff in, we caught 1,000 bugs. Great. We fixed the 1,000 bugs. Now what? What are the contract checks doing? They're checking a program that's correct. Bear with me. If you've put the contract checks in and turned them on, and everything is being checked internally throughout your whole system, and you run it for a year, and you never once get any problem, you might want to turn them off. In fact, you might even want to assume them and get even more performance. This is not something you have to do, something you can do. And what contracts give you is something that varies with industry, application, program maturity, part of a program. It's all moving. And contracts will in 29 give you the ability to change any one part of your program to be checked or not. Does that make sense? So it's really useful to have contracts, because if you don't have contracts, it's always checked forever. That's not what we want. Okay.
Herb mentioned in his keynote the importance of being able to do this just by recompiling. And I think that touches on something you said with wanting to keep safe from people wanting to use other languages. Because if I have to write or change my code in order to adopt this, then I'm tempted to think, well, if it's a rewrite, I'm going to look at other languages. How much of this can be done just by turning on new compiler flags and just recompiling the existing code?
Okay, so there are two ways in which contracts can help us tremendously without having to do any work at all. Number one, contracts in the core language will allow us to check things like null pointers, C array style bound checks, all of that stuff. Absolutely, right? We can do that. Then in the library, there are all of these potential checks that we could turn on. This is a property of the particular vendor. So a particular vendor can give you the ability to check any undefined behavior, right? And you can turn it on. And then without doing anything but recompiling your program, you get this enormous amount of checks at the very lowest level of your system. And you know what? All of that, it's not just this part of your system. Even if you write all this stuff up here, it all comes down to this, the standard library and the core language. So just by recompiling, you get an enormous amount of vicarious checking. But then you also get the ability to write your own functions and check your own functions. And that's something you might choose to do. And if you do, you'll get paid back for it. But if you don't, you still get all of this checking. So contracts in the language, contracts in the library, implementation is a wonderful passive thing. You'll still have library undefined behavior in your own code. If you call your own library from your own library and you mess it up, that's on you.
Hi. You talked about the law of exclusivity, and you showed an example from the circle compiler.
Mhm.
Do you think it would be possible or desirable to have law of exclusivity enforcement in the core language?
My exclusivity
Law of
enforced.
exclusivity enforcement in the core language. So the law of exclusivity that
Yes.
you showed the example from the circle compiler.
Yeah.
Do you think that would be a desirable thing to have in the C++ core language in a future version?
Well, I don't know enough about it to talk about it with any great detail because Sean Baxter is the wizard of all things, and from what I understand, in order for us to do this, we have to have our own standard library. When you ask in the core language, can you give me an example of what you mean by in the core language?
I mean, so we get effectively Rust-style borrow checking in the C++ core language.
Okay, so we've done a lot of looking into that. The trouble with the Rust style borrow checking in the core languages, it requires us to rewrite a tremendous amount of code. And so the answer, I guess, ultimately is it would be nice if that were available, but it doesn't seem like it's going to solve the general problem. It's not going to be adopted because we would need a separate SDD2 and we'd need to do a whole bunch of stuff to make that work. The nice thing about ghost data is that it takes the idea, it turns it into runtime, and it leaves us to have all of the algorithms and all of the original vocabulary types stay in place. So I think if you want compile time checking, you have to write your code a certain way. And we have many, many years of C++ already written, already out there. And so for brand new people who want to do that, they can't. But for us old people who have been around for a long time and written a lot of code, like Microsoft and Bloomberg and Google and A9, for example, there's just so many companies, and it would be really nice to be able to continue to use C++ in the style and in the way and in its full glory, rather than sort of crimping it into a particular style that's quite different from what we're used to programming it. I don't know if that helps. I mean, we have Rust. So if you want to write code in that style, which is a very different style, you can. But the idea is to take the massive body of code that we have in C++ and make it work. I mean, I hope that answers your question.
Thank you.
I know, but I didn't realize when you said in the core language, you meant borrow checking. And yes, we've looked into that, and that is the issue, adoption. Okay. Yes.
So when I look at the code base of my company here, significant source of annoying bugs is databases. And one of the nice security features of global checking and parse is that it can implement databases.
Absolutely.
And we will never get this to C++.
No. Well, I'm not saying that at all. What I am saying is that there are a large number of things that we need to tackle, and with all of the different. Let me see if I can. Remember this picture? Well, much later we have a picture that shows that we will get to all of it.
That's exactly what I'm asking. If
Yes.
can exclusively checks by at compile time, like at the same power that was provides.
But our goal with yes, yeah. This is the picture. I think this is the picture you're talking about. This is a good picture. The goal is we can get this with compile time, but we can get all of it with runtime checking, because runtime checking, I'm going to get flack for this. Runtime checking is more powerful than compile time checking because it can address everything that can be addressed at compile time, plus what can't. You see what I'm saying? So the way runtime exclusivity works, the way that works is it keeps track separately of the information at runtime, whereas the compile time exclusivity makes sure ahead of time that it just can't happen.
And I want to have compile time exclusively, like we have in parse with the debate.
Okay, so I do too, but I can't make it happen for all algorithms. Everybody understands, right, that Rust, oh my goodness, Rust works because you do a subset of what you can do in C++. That's why it works. So I showed an example earlier when I was really feeling ill. Sorry about that. I'm feeling a little better now. I showed an example where, let's go back and look at that. This is worthwhile. So we had this example. So let's look at this example again. We have this guy here. All right. This is an example where we can't do this in Rust. We can't write this code because it could be a problem, right? Now, if we reserve this, it's not going to be a problem. But we still can't do it. This is not allowed in Rust. Does that make sense? It's not allowed. Yes. It's allowed with what? Unsafe. Okay, hold on. Everybody knows what I'm going to say. Yes, unsafe Rust is not better than C++, is it?
But in the intent, right, we are saying that that small space of code is the source of the error. And it could be the source of the error.
Oh, okay. I personally don't buy it. My experience at Bloomberg, which is vicarious, is that people use it almost all the time. They use Rust, but they do not use safe Rust. They use unsafe Rust. That doesn't count. That's like wearing a mask on your chin. I mean, listen, Rust is fine. If you have the discipline and the intelligence to write all of your code in a way that it can be checked at compile time, I'm all good with that. My problem is I'm not good with it's being checked. I'm not good with it if I can't check it at compile time. I have a huge corpus of code, and what I want to do is leave the code in place and verify that the code as written isn't executing undefined behavior. Now think of this glorious thing. The goal is not to execute undefined behavior. It would be nice if you could look at the program and go, this will never execute undefined behavior. But that problem is too hard. So we have this other problem that says, I want to make sure that this program never executes undefined behavior soon. Not immediately, but soon. So you have all these checks in place. You run the program, like you test it. You go, oh, look, it's broken. You fix it, and it gets better. Does that make sense? Once the program is fixed, you don't need to check it every minute. Now, in Bloomberg's situation, we have thousands of processes running doing the same thing. What if we had 4 of those 1,000 running in check mode, so they're really slow, and all the rest are running really fast? And all of a sudden we see, something bad happened over here. So we put in a ticket and fix it.
So when you said checking it compile time is too hard. So you said checking it compile time is too hard. The problem with checking it compile time is too hard, right?
The problem is we can't check there are many programs that cannot be checked at compile time, but they can be checked at runtime. Hence, runtime exclusivity is doable.
That's great, but for example, dependency checker would rule out that this database on the data.
We'll do what?
In Rust, dependency checker would make sure there's no database on the data. It's impossible.
Right. That'll do that at compile time. We know that. For some algorithms,
You're not going to get that in C++. That's what you're saying.
we're not going to get that in C++ because C++ is written differently than Rust. Rust is written in a very constrained way. So if you want that kind of checking, you have to write things in a very constrained way. C++ has much more latitude to write things in other ways.
Could we possibly introduce a new C++ profile that restricts the language? Just asking.
Okay, so Sean Baxter with Circle has done that. Yes, it exists, of course. I'm not saying there's anything wrong with it. Don't get me wrong. Yes.
Hi. Oh, sorry. I kind of get the compile time checking, all right? You're going to get a compilation failure. What about for contracts? Like so when you run time contract checking, it's obviously only doing it on the values passed that are passed to that function. What is the defined behavior of failing a contract while runtime checking? Is it to terminate or is it to just?
Okay, so let me explain what's going on with contracts. This is great. This is better than anything I had prepared. This is wonderful because I feel like I can talk to this. So contracts have 2 very important things. They check preconditions, postconditions, and conditions inside your function, which is contract assertion. Okay, that's the 3 things. Now, separately, you can control what happens. Now, today, it's on a translation basis. So and it's a little bit funny. So it's not going to break. It's not undefined behavior, but it's not predictable in 26. You have to get used to the idea that if you're going to turn on contracts in only part of your program for some of your translation units, you're not really sure whether it's going to get checked or not. Okay? I know. I mean, you know what I'm saying? You have to be a little bit savvy about how compilers and linkers work to know what's going on. But it's not a big deal. In 29, we'll be able to be very specific and say this contract check will be on or off depending on certain conditions that we control outside the program or inside the program using something called labels. So imagine that we have a master control outside the program, and when we build it, we say we want exactly these checks on and whatever. Okay, now, the next thing is we have what's called a contract violation handler. So it's a callback. So when you have a particular error or whatever, when you want to assign a semantic to a particular check, there are 4. Okay, there is ignore, which means nothing happens. There is observe, which means the callback is called, does whatever it's going to do, typically prints the error, comes back to the call site, and then continues. That's that. Then there's enforce. Again, the callback gets called, and then if it comes back to the call site, and by the way, there's one callback. I want to be clear. There isn't a callback for each thing. There's one callback that you install as the owner of main. That's the thing that happens. It's the handler. Okay. Comes back, and if it comes back, terminates. So that's enforce. There's one more semantic which we need for scale called quick enforce. So if you have quick enforce and the predicate is false, it traps. It's done. Very efficient, very quick, get out. Does that answer what happens? Because what happens is configurable during your build. Does that make sense? Okay. Again, not every program has the same level of security. Some people will want to trap because they need fault intolerance. So if something is wrong, you have to fail fast. If you're in a financial institution, you'll want the callback to save all of your stuff, transactions, close your databases, and terminate, likely. If you're a video game or some other thing, a desktop publishing, you're going to want to save all your data, maybe report something to your customer or not, maybe write home to the factory, and then continue even though you know it's undefined behavior. Why? It's been working up till now. We don't want the customer to complain, so we're just going to do it. All of these are valid things to do. Does that make sense?
Is there a way to continue with defined behavior then?
And do what? What would you want to do? Terminate? Continue? I mean, you can do whatever you want. It's undefined behavior. Right? I mean, I don't know. You understand, it depends on your industry. Are you flying the space shuttle? Are you playing a video game?
Well, I mean, I'm kind of referring to your pre and post conditions where you say like, oh, is it within the bound? And if it's not within the bound, then it's undefined behavior.
Correct.
When
you say, can you return, what do you mean by return?
I suppose it depends on the case. But
Of course it does. The thing is, in a correct program, this never happens in a correct program. You get to a point and somebody says, this is not right. You have to decide, do you want to continue? Is this a program that's been working for 10 years and you just added contract checks? If it is, continue. If this is a program that you just wrote and you're about to put it out to production, abort, fix it. You see what I'm saying? It depends. It really depends. The beautiful thing about contracts is that it's all things to all people, and the person who's writing the program and composing the libraries gets to make the decisions. I hope that, yeah, okay.
Hi. One question about the contract. So, as far as I understood, they so they can work at compile time. That's fine with me, but can also work at the runtime, and thus they will impose some kind of the runtime checks, right?
Okay.
And
Contracts are primarily runtime checks.
yes, and
Yeah.
with runtime checks, I'm getting a bit nervous the amount of code that they would generate. I understand that the amount of code can be quite negligible, but still, do I have any kind of the control except for disabling them properly? Because you mentioned like four types of control of them, but can I control them in a more local way? So, for example, if I'm using the standard library, which will start to use contracts and operator X of the vector element now checks the index, and I'm writing my own algorithm that uses that operator, that uses a vector. Can I say somehow that I'm okay with bypassing these checks in
Okay.
some kind of a local way.
So the question is, how much granularity do you have over controlling contract checks? In C++26, it's by translation unit and not very good. But that's okay, because it's better than nothing and you'll get to learn to use it. In 29, which is really important, you'll be able to specify each and every check outside. So if you want to control each and every one individually, you can. Does that answer your question?
Yes.
Okay, good. We need that. But you can't have everything. It's called a minimum viable product. And this is more than minimal. And we also had to take out inheritance because the folks did not all agree that the inheritance model needs to be more flexible than what people think Bertrand Meyer's design by contract rules are. Well, that'll open up a whole can of worms if we talk about that.
I wanted to understand what would be the runtime implications of runtime contracts. Let's say if I use a runtime contract versus if I just add conditions,
Add,
like normal checks in a function.
I didn't understand, using runtime contracts versus
Just normal checks, if else checks. So,
normal checks, meaning like just check the thing with an if statement. Okay, there's no difference. It's the same thing, because what are you doing? You're checking a predicate with an if statement or whatever. The code's the same. The point is that the code is controllable. There's no extra cost. The code is controllable so that if you want to check it, you can check it. If you don't want to check it, you don't have to check it. If it's an if statement, you have no choice.
and how would that like behave if we introduce ghost data into it?
I'm sorry, say again?
How would that affect if, let's say, ghost data?
So ghost data doesn't exist yet. We're working on it. It's a research project. But basically what it's saying is, let's defer our evaluation from compile time to runtime. So we're waiting until runtime. Okay? It's more expensive at runtime. But the beautiful thing is you get to use any algorithm you want. And at the point at which you screw up, it tells you. Do you see what I'm saying? So in the case where we had the thing that says, no, we can't do that at compile time because it might screw up, at runtime, we wait until it does screw up, and then we complain. Do you see what I'm saying? So it makes sure that we don't actually have a problem, not make sure that we don't might have a problem, if you'll excuse the English. Okay. Anything else? No, we have a question. Okay.
Yeah, I have a question about contracts. So let's say you have two functions f and g, and they call each other, and they also call each other in contracts like post conditions or whatever. And there might be some sort of recursion there. So in like when you check in post conditions for f, you call g, but each inside calls f, which inside calls g. Is it like anyhow solved or?
Okay, so the question that, as I understand it, is, does recursion present a problem? So far, I don't see any reason why it would. Because what are you doing? You have a check at the end of your function. So you check it each time you return. And by end, I mean when the function comes back, right?
Yeah, I have a check in the end of each function. So let's say my f comes to the end of its execution. It checks, like it runs g function again, which in turns runs f again, which in turns run like g again, and so on. So like it's gonna be like infinite recursion or.
So yes, I understand, but the predicate that checks the pre and post condition is going to be invoked each time. As long as the predicate is successful, are you saying it might be expensive?
I'm saying it might be infinite if you're not, like if you're reevaluating everything again and again as a post condition.
But each time the function returns, it might return with a different value, right?
I think he meant that the function is called inside the post condition check. So that if you put functions inside post condition checks, to me it sounds like it's just a Stack Overflow like we have been used to.
I think it's a plain straight up bug if you do what I now understand what you're saying, right? You're creating an infinite recursion,
Yeah.
and that infinite recursion might occur only when the check is active, right?
Yeah.
Don't do that. Okay, that was an interesting question. All right. Anything else? Okay. These are great questions, by the way. I'm really glad I went through the first part quickly when I was dying so that I could actually answer some useful questions.
Let's say in your project you've got a lot of requirements like Israel or something similar, and you want to control those with contracts. In order to verify easily for a given code base, like a large code base, can I declare, oh, I know that I'm setting this contract, I don't have to check my compiler flags, so just compiler flags right now.
So I guess I didn't quite get the beginning of it. You're saying you have compiler flags. That's how we control things right now.
I'm saying, say you've got like a coding style guide, or security guideline like Israel or something, and you want to enable certain contract checks to help you.
Yes.
Is there a way to like audit or verify that easily? So I'd have to like just look to see what kind of flag I'm setting, or is that the only way to do it right now?
So, right. So it might be the case that you have different compiler flags for different compilers. What we're trying to do is normalize that so there's sort of one way to control these things. Does that make sense?
In your real world case, I'm presuming Bloomberg's use of this is fairly more advanced than C++ 26 or 29. Do you run this in prod, or do your current system, are they running it in production, or do they always run it in test?
So we can't use C++ 26 contracts because they don't have the granularity that we need yet. Soon, we will, in 29, have everything that we need to transfer over to 29 because that will be sufficient to handle everything that we need. But we've been using something that's very basic, macro-based, since 2004 in production, and it works beautifully. The problem was that when we had enforce only, what happened? We had a bunch of code, it's working in production, not all of it is contract checked. Then we put some new contracts in, and contract checks in, and then the code broke in production. And so there was a pressure not to put the contract checks in because they would be enforced. So we realized that we absolutely had to have what we call review, which is the same length as assert. But we need an observe semantic. Now, when we add new contracts in production, we observe them. They report an error and continue. Oh my God. They continue even though that some contract is allegedly violated. It might be benign, it might be pedantic, it might be real. But, if you shoot into a house and it hits a stud, you're lucky, right? As long as you don't move the gun, keep shooting at the stud, you're okay. If you do something and it misses it, you could cause a real problem. The thing is, the contract check detects that you're hitting the stud. We go in and look at it and fix the problem, but we don't cause all of our customers to go away, to crash. So this is a good thing. Yes? Okay. These are great questions, by the way. I love it.
Hopefully 2 quick questions. You mentioned you have perhaps 1,000 processes, 4 of them running the contract checks. As you've got that direct comparison, can you give us an indication of what performance overhead that introduces? I know it all, how long's a piece of string, but what is the comparison?
Well, it's hard to say because here's the thing. We can run what we call default checks, and then There's something, this doesn't exist in C++ 26, but it will exist in 29. So for those checks that increase the big O complexity, we probably wouldn't run those in production at all. We might, who knows? Because they're those 4 little canary things, even if they didn't run at all, the thing would still work. These are more for gathering metrics. So how much would that affect? It depends on how many you turn on, right? If you turn on just we have what's called optimized checks, where we know that if that goes wrong, we're really in trouble. And so that's kind of like we leave those on pretty much all the time. Then we have the default check. It's kind of like a bell curve where there's 1% that you leave on all the time. Then there's 98% of them that you turn on when you want checks. And then there's like another 1% out here that are quadratic or something really nasty that you turn on only for an audit. Okay? So that's how we do it. So the answer to the question is, depending on how much you turn on, it will be more. But hopefully, we hope it won't be more than, let's say, twice as expensive. Do you see what I'm saying? So they might run at half speed. Just to let you know, some people don't optimize their code so that when their program crashes, they can debug it. That's 10 times slower. This is better than that.
And related to that, do you ever, it might be too early to tell, but do you ever find the optimizer will just optimize away checks? And I guess if they don't does that mean that they weren't needed or the contractor's already passed anyway?
I hear, yeah. Do I ever find that that things, well, you know, here's the thing. The optimizer isn't allowed to change the meaning of the code. So it's called the as-if rule. If the optimizer does such a thing, that's a bug, right? Because it can't change the meaning. So if it takes it away, that means that it didn't do anything. That's the best I can tell you. And my answer is no, I have not found that. But if it did, that would be bad. Yes, sir.
Because the word granularity sounded a couple of times already. My question would be, what are your thoughts how to implement that granularity? So basically, what kind of control, local control your caller will have to control the checks inside the core?
Yes, I'm happy to explain that. So the way we've thought of this is something called labels. So what is a label? Every contract check, what does it have? Pre, post, contract assert, right? Then it has a predicate. That's all there is. That's the meat of it. That's what tells the static analyzer and everybody else and the human being what must be true here, whether or not it's checked. Then outside the translation unit, you set everything for the translation unit. Now imagine that you could put an arbitrary name next to it. Imagine you could put a set of arbitrary names. Suppose those arbitrary names had meaning, then we call them labels. Now you could have a label that says, specifically, I always want you to enforce. That's a possible label. You could have a label that says, John did this, and we're gonna enable all the things that John did to be enforced. So in other words, using labels, and then here's the secret, there's going to be the equivalent of a environment where you program the environment using the compiler flags, and then the environment defines what the labels do. So we have 2 levels. So imagine the C++ standard has the environment and the labels, and that has a meaning, it has its own understanding. And then the interface between the outside world and the environment is a well-defined way to set those values. And that's how.
Thus, it creates another layer of interfacing with the entity, with the class, with the compound unit. Because as soon as you define these labels, it becomes an interface.
Yes, yes.
It needs to know at least what labels are.
Exactly. So the standard will define what the labels mean and how to use them, and then the implementation will provide the user flags to set the environment, but those will be few. They'll be like set label to this, And that means that the interface is much cleaner than having everybody do everything, right? That's a great, love that. I think we have time for maybe one more question. If anybody has one? Are we all good? Okay, last question.
Hello, thank you. My question is that you mentioned that contracts doesn't bring any side effects by default, but an advanced view on that is that there are no dangerous side effects.
That's correct.
And the question is, are order of execution of prayer checks and post checks will be defined by the standard, or it will be like subjective to the compiler?
Wait, the order of checks? Do you mean if you list them out pre, post like that? I'm trying to remember. I believe that the order is the order in which they appear, the lexical order. Right? So in other words, if you say pre this, post this, pre this, the post obviously, you understand, yeah. But modulo that, yeah, it'll be in that order. So all the pre's will be in lexical order, all the posts would be in lexical order. Why you would interleave them, I don't know, but you know.
Because compiler, I believe, can reorder the if checks if we get to the previous question that basically it's not more than just an if check the way the syntactic should be about. And compiler can reward it.
Well, I don't believe it can. I don't believe that's allowed for the contract specification. I will tell you that if you have dependencies in the precondition, some people get worried, like you'll have a precondition that says, is the thing, is the pointer null? And then does something the pointer to, is it greater than 0? And they're dependent checks. That's actually not something that we would like to see happen, because we want all of our checks to be independently controllable. That would be ideal. And that way we don't have any issues. But every single check, whether it's checked or not, must be true in a correct program. And typically when you have a null pointer and it must not be null, the program needs a null pointer and it will die anyway. So whether it dies in the precondition check or it dies a few milliseconds later in the program, it's still a bug. Not something to worry about in general. All right, I think I'm out of time, and thank you very much for coming. I apologize for not feeling well in the beginning. I hope that is helpful. Enjoy the rest of the conference.